Welcome back to Remote Sensing Applications using ArcGIS. In this video session, we're going to look at something called the spectral response. And basically what we're going to do is look at the spectral response along a topo sequence. And sometimes the spectral response or spectral relationship is not what you expected due to confounding factors. So for example, for your nanana.tiff image, display it as a color infrared image, so band 432 controlling the red, green, blue video intensity, and apply a 2 standard deviation contrast stretch. And then add to this data frame a shapefile called Topo Sequence, and then assign some symbol to these 3 points along this Topo Sequence. So here's our Topo Sequence, so I can right mouse click and zoom to layer on my points layer. And it's basically going from an area down on the Tanana floodplain region, up the hill slope to a mid slope, and then up at the top of the slope. And if you go to the properties for this point layer and go to labels, we'll label each feature by a text field called location. And let's give that a 14-point font. So basically we've got this alluvial site, a mid-slope, and an upper slope. And since the shortwave infrared bands are strongly controlled by moisture, you would expect this alluvial site, which is a moisture site, to have relatively low shortwave infrared values. And as we go upslope, the shortwave infrared values would become higher and higher as we would expect moisture to become less and less as we go upslope. So what we're going to do is use the sample tool to get the pixel value where each location is. So what we'll do is we'll first add to the nanana frame from the nanana.tiff.image band 5, which is the shortwave infrared. So there's our shortwave infrared band. And then we'll use the sample tool to sample the pixel values from these 3-point locations. And let me zoom out so you can see these 3-point locations. Okay, so we'll use the sample tool. So for every location in our Topo Sequence point features, go to the pixel from this band 5 and extract its value, and the results will be in this DVF table. Okay, so here's our original Topo Sequence point attribute table, and the sample tool extracts the feature ID, so our Topo Sequence feature ID 0, 1, and 2, and then this is the shortwave infrared value along this Topo Sequence. So as we're going up the hill slope, the shortwave infrared value is decreasing, which is the opposite of what we expected. What we expected is as we go from a moist alluvial site to mid-slope, it would become drier and the band 5 value would become brighter all the way up to the upper slope. So basically what is happening is we have confounding variables that are influencing this relationship. It's not just moisture. So one confounding variable could be canopy density. So for example, down here at this alluvial site, it could be a fairly young, dense stand of balsam poplar in the sapling stage, so very high canopy density. And that would lead to a higher shortwave infrared value, as opposed to up here, it could be a mature birch stand with shadowing in between the mature canopy crowns, leading to a lower shortwave infrared value. Another confounding factor could be slope. So for example, here we're on an alluvial floodplain, it's flat, and here we could be on a slope that's facing away from the sun. So it could be a slope that's sort of in a northwest or western slope. So the sun in this example is in the southeast, So the brighter slopes would be facing the southeast, and the darker slopes would be facing northwest or west. So topography also can be a confounding factor. And if we look at the difference between a Site 1 and Site 2, Site 2 has a very low shortwave infrared value, and that's likely due to two things. One is this is coniferous vegetation, so there's lots of shadow in between the crowns of the individual spruce trees, and then also this is a steep north-facing slope, so there's lots of shadows associated with topography. So the two confounding factors here are vegetation type between these two sites, and then also the influence of topography between these two sites. Okay, what we're going to do now is look at the spectral response of two different vegetation types that are very different. And one is a floating vegetation called buckbean, the genus Manyanthes. So here's an example of this floating mat of buckbean. Compare that to aspen birch. So here's an example of a fairly young aspen birch stand. And they're both broadleaf vegetation types. It's just that the aspen birch are forest stands in the uplands, and the buckbean is a floating mat in the lowlands. And if we look at the canopy, here's an example of the aspen canopy, so quaking aspen. And here's an example of the buckbean or Manyanthes canopy. So basically it's a floating wetland vegetation that is a broadleaf plant. So we've got two broadleaf vegetation types. One is a wetland floating Manyanthes bean, and then the other is the upland forest of aspen or birch. Okay, if you create a new data frame and add to that data frame a point feature class called broadleaf canopy. So this will be 10 locations that are aspen birch and 10 locations that are buckbean. So we could symbolize those by going to the symbology tab and then categories, and then by vegetation type, add the different values of vegetation type, and then uncheck all other values. And then you could symbolize aspen birch, whatever symbol you want for aspen birch. So I'll give this a size of 8 and a color of some green color. And I'll give the buckbean a size of 8 and a color of some peacock green, whatever symbology you want. And then what we're going to do is add a Landsat 8 sensor image. So that's going to actually have 6 spectral bands that are all reflective bands. So we'll add that as just a TIFF image. And then we'll symbolize this so it looks like a color infrared image. So once again, that would be 4, 3, 2. So 4 is the near infrared band, 3 is the red band, and 2 is the green band. And then we'll assign a contrast stretch. So our contrast stretch will be standard deviation 2. So you can see that indeed here we have, these are all in bright red areas that would be aspen birch, or down in the floodplain in the wetlands area, these are all in bright red areas that are floating mats of buckbean. Okay, so what we want to do is sample the pixel values within 50 meters of each location of an aspen birch location, and within 50 meters of each buckbean location. So run the buffer tool to create 50-meter buffers, and then you'd have something like this. So around each location we have a 50-meter buffer. So we'll have 20 buffer polygons, 10 for our buckbean locations and 10 for our aspen birch locations. So the next step is for each spectral band, we want to know what is the average pixel value inside each of these 20 buffers. To answer that question, we're going to use a tool called zonal statistics as table. But first, what we'll do is add the individual bands as separate layers. So if we go to our data frame and we'll go to Landsat 8 and double click on it, and we'll add these as separate layers. So if I hold Shift key down, I can select all 6 spectral bands. And then I'll collapse all layers. And then what we'll do is we'll just rename these layers so they have a simpler name. So band 1 through band 6. Okay, so then we're ready to run the tool zonal statistics as table, where our zone will be each canopy buffer represents a zone, and then we'll run the tool on each of these 6 layers. So since we're going to run this tool 6 times, we're going to run it in batch mode. So if you right mouse click on the tool and select batch, and then we set up our batch mode. So our input feature zone data is our canopy buffer, and the zone data will be the ID of each polygon. And then our input value raster will be band 1. And then we'll output to wherever we want to output to. So I'm going to output to my data folder, and I'll call this band 1 stats.dbf. And then we simply will select this row and then hit the plus button to copy it. And we're going to copy it until we get to the 6th row, because we have 6 spectral bands. And then all we have to do is change this band 1 to ask the same question for the 2nd band, the 3rd band, the 4th band, all the way through the 6th band. And then we simply rename our output table. So the second time through, it'll be band 2.stats, all the way down to the last row will be band 6.stats. But before we run this tool, what we want to do is request for our statistic type mean. So we want the average value within the buffer for each buffer. So for each of these bands, just give us the average value inside the buffer for all the pixels that are inside the buffer. So I could copy this, Control C, and then I could paste it, Control V. Okay, and since I requested the mean, I went back and I renamed this table, so it's band 1 mean.dbf to band 6.dbf, just to give me a more meaningful name for the table. And then we could run this tool, so okay, go and run it 6 times. Okay, so that gives us a table for each buffer ID, how many pixels were in that 50-meter buffer, what that area that was, and what the mean value was for that spectral band. So now what we want to do is we'll add a field named band and then calculate the appropriate band number for each of these 6 tables. So since we have 6 tables, we'll do this in batch mode. So once again, if you go to the tool, right mouse click, choose batch. So our input table, our first input table will be band 1 mean. And we're going to add a field called band. And we'll make that a short integer field. And then simply select that row and then hit the plus button to add another row. And then we simply say, okay, our second row will be associated with our table band 2 mean. The third row will be band 3, and the fourth row will be band 4, and the fifth row band 5, and then the last row band 6. And then OK, we'll add this field name band to each of these 6 tables. Okay, so now we've got this field name band for each of these 6 tables, so then simply use the field calculator to assign the appropriate band number for each table. So for example, this is band 1 mean, so I'm going to just calculate that as having a value of 1. And then the next table, band 2 mean, I'll simply calculate that as band 2, etc., all the way up to band 6 mean. Okay, so now each table has the appropriate band number. So this is band 5 mean. It has the field value for the band field, a value of 5. This is band 6 mean, so it's got the appropriate value 6 for its band number. So then what we could do is use the merge tool to merge together these 6 tables into one table. Okay, so then we've got our 6 tables as the input, and I'm going to output this to a new name called mean values band 1 through 6.dbf. And we really don't need the area field in our output table, and we really don't need the count field in our output table. So we simply have the ID, which is the buffer polygon ID, the mean value for that band, and what the band number is, and then just OK. So now we have one table for each of the 20 original locations. We buffered them by 50 meters. What's the average value inside those buffers for band 1 all the way up to band 6? Okay, the next step will be to use a tool called pivot table that will allow us to rearrange our table, so then we could use it in a spreadsheet like Excel. Okay, so this pivot table tool allows us to rearrange a table. So our input is this mean value bands 1 through 6, and the first thing is the input field. And that's going to be the field that defines the row in our output table. So we'll have for every ID, it'll be a different row. And then the second thing is the pivot field, and that will define the columns in our table. So we'll have columns band 1, band 2, band 3, band 4, band 5. And then the value will be the mean. And then I output to, I just call it pivot table.dbf. And then we'll just go OK and execute this tool. So here's our resulting pivot table. We have for our rows each of the original 20 polygons, and for our columns our 6 spectral bands. And now we'll use this pivot table in the Excel spreadsheet to look at, is there a difference between the 10 aspen birch buffers compared to the 10 floating mat buckbean buffers? So we'll exit out of ArcMap, and we'll open this pivot table.dbf with Excel. So open with Microsoft Excel, and then we'll save it. So we'll save it as an Excel spreadsheet. Save as Excel workbook. Okay, so the first thing we'll do is we'll assign the format for these columns. So if we right mouse click, format cells. So for number, no decimal places. The original bands were just integer values. And that gives us visible integers that we can see in our table. And then we'll just save this worksheet. So the question that we're trying to answer, is there a spectral band where there was a difference in the values of buckbean compared to aspen birch? So you remember stands or polygons 1 through 10 were buckbean. So we'll color that some color, darker color. And then 11 through 20, those are aspen birch polygons. So we'll give them some other color. And then we'll add a row. So right mouse click, insert. to separate. And one more, insert. Okay, so what we want to know is what's the minimum value within the 10 buckbeam buffers for each spectral band. So we could put in a text min buckbeam and then use Excel equals minimum, and then we select the 10 values for band 1. And then repeat the process for all the spectral bands. And then the same thing, what was the maximum value for buckbeam? So max buckbeam. And then for our first cell here, it's going to be equal to maximum. And then select the 10 spectral values for band 1. And then we repeat the process for our aspen birch stands, minimum value for band 1 through 6 for aspen birch, and maximum value for band 6, 1 through 6 aspen. Okay, so then once that's accomplished, what we'll do is save our work, and then we'll develop a plot plotting the minimum spectral band for buckbeam and the maximum spectral band values for buckbeam compared to the minimum and maximum for each spectral band for aspen birch. So we'll create a plot, and it'll be a scatter plot, and then select data. So we'll add, and the series name will be buckbeam minimum, and then the X values will be bands 1 through 6. And the Y values will be what the minimum value was for buckbeam. And then just repeat the process. So the next one will be add, and this series name will be buckbeam maximum. So basically repeat the process for buckbeam minimum maximum and aspen birch minimum and max. And what you should get is a relationship like this, where the green dots represent aspen birch minimum and maximum. So for example, this is aspen birch. Of the 10 aspen birch buffered polygons, this was the one minimum of those 10, and this was the one maximum of the 10. And then I symbolize the buckbeam min-max using an open square. So for example, here's an open square representing the minimum of the 10 buckbeam buffers, and here's an open square representing the maximum of the 10 buckbeam buffers. So there's very little separation between these two cover types, and that's probably due to confounding factors such as density with the buckbeam. So if you don't have a completely closed canopy, in between the buckbeam leaves would be water, which would dramatically reduce, for example, the shortwave infrared bands. And if you have a closed canopy, that would increase spectral brightness in most bands. And the same thing with aspen birch. One of the confounding factors could be slope position. So for example, a southeast facing slope versus a northwest facing slope be confounding factors. And if we look at the spectral response by bands, here's the visible bands of blue, green, and red. So these are both photosynthetic canopies where chlorophyll is absorbing in the red spectral region and chlorophyll is absorbing in the blue spectral region. But because the blue spectral region is the shortest wavelength, it has the most atmospheric scattering. So basically the blue spectral response is inflated due to atmospheric scattering. If we were to look at it on the ground, we would find the blue spectral response would be about the same level as a red spectral response, and the green would be slightly higher than the blue or the red in the visible. And then since we're dealing with photosynthetic broadleaf, the highest values are from the near-infrared spectral region. And then we have lower values from the shortwave infrared spectral region. Okay, so if you go to the Blackboard website, there's the remaining quiz questions for this week's video sessions.